Hi everyone, myself Konda Krishnudu, Assistant Professor of Physics, Department of Science and Humanities, MLR Institute of Technology. In continuation to previous topic, today I am going to discuss about one of the interesting phenomena that is associated with ferromagnetic materials, that is hysteresis. Coming to overview of today's presentation, today I am going to talk about introduction to magnetic materials, after that basic introduction to domain theory, then hysteresis, explanation of hysteresis based on domain theory, and then conclusion. So coming to introduction to magnetic materials. So before going to discuss the actual topic, we need to know that all materials are broadly classified into two types based on magnetic property. They are magnetic materials and non-magnetic materials. The materials which responds to the applied magnetic field are called magnetic materials. The materials which does not respond to the applied field is called non-magnetic materials. Actually, magnetism has atomic origin, means atoms of the material will decide whether it has to act as a magnetic material or not. So we know every substance is made up of its basic constituents called atoms. So each tiny atom itself acts as a magnet, having magnetic moment. The magnetic moment of all atoms will add up and will give rise to net magnetic moment. As a result of that, the material will get magnetic property. Based on that, all magnetic materials are divided into 5 types. They are diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. All these classification is based on the response to the applied magnetic field. So out of all these materials, today particularly we are going to talk about ferromagnetic materials. Ferromagnetic materials have some special properties when compared with other magnetic materials. They are strongly attracted by the magnetic field, means their response to the applied field is very fast, very strong. The second property of magnetic materials is that they possess spontaneous magnetization. Spontaneous magnetization means even in the absence of applied field also they will have some sort of magnetic moment. Coming to another important property is that they are able to change their state from ferro to para state. Both para and ferromagnetic materials have same properties, but the magnitude of properties in the case of ferromagnetic materials will be more. When we heat ferromagnetic material, it will lose the properties, so that it will make a transition from ferro to para. And one more important property or characteristic of ferromagnetic material is that it has small effective regions called domains. So these are the special properties that are associated with ferromagnetic materials. Because of these special properties, ferromagnetic materials have many applications in many fields of science and technology. Like they are used as electromagnet, they are used as magnetic storage devices, they are used in hard disks, loudspeakers, telephones, hard drivers, and magnetic tape recording. So like that, ferromagnetic materials have very important place. Now coming to the phenomenon called hysteresis, for that we need to talk about domain theory first. Using domain theory only we need to discuss hysteresis. What is domain theory? So according to the scientist Weiss, a ferromagnetic material has large number of small regions called domains. Each domain size is around 10 power minus 6 to 10 power minus 8 meters, means very small. Each domain will have around 10 power 17 to 10 power 18 atoms. Each domain is self-saturated. Each domain is self-saturated, means atoms in that particular domain will give rise to net magnetic moment. For example, take this a ferromagnetic material. In this ferromagnetic material, so many domains are there. This is one of that such domains. Magnetic moments of all tiny atoms in that particular region will add up and will give rise to large magnetic moment. So that is why you can say that each domain is self-saturated. But the magnetic moment direction is different for different domains. So that we can observe. Take this domain, its magnetic moment is in this direction. Take this domain, this magnetic moment is in rightward direction. So like that, the magnetic moment of all the domains will be different in the absence of applied field. That is the situation we are seeing here. So that is brief information about the small effective regions that are present inside a ferromagnetic material called domains. So what happens when we apply magnetic field on a ferromagnetic material? So this is the case when in the absence of magnetic field, when the applied field is 0, in that case all the domains will orient in random directions. Magnetic moment of one domain cancels with the other, and hence the net magnetic moment is 0 in the absence of applied field. What happens when you apply magnetic field? When we apply magnetic field on a ferromagnetic material, magnetization takes place by two processes. One is by domain displacement, the other is by domain rotation. So domain displacement takes place when the applied field is weak. So initially when we apply small field, magnetization starts in a ferromagnetic material. So that magnetization comes under this category, what is called magnetization due to domain displacement. When we increase the applied field, when we increase the strength of the applied field, in that case what happens is all the domains tries to orient along the applied field direction. So by seeing this figure, we can say that when you apply magnetic field in this direction, out of all the 4 domains, only those domain which is orienting along the applied field direction will increase in size. Increase in size means we need to understand that magnetization is taking place in this particular domain. So those domains which are moving in the favorable direction of the applied field only will respond and magnetization takes place. That is what is called magnetization due to domain displacement, which takes place at weak fields. Now what happens when you apply strong field? When you apply strong field, in that case magnetization takes place by domain rotation. So what is domain rotation? So by this figure we can understood clearly, when you apply strong field, all the domains will respond to the applied field and they tries to orient along the applied field direction. That is what is called magnetization by domain rotation. So that is how magnetization takes place in a ferromagnetic materials by two processes. Now the actual topic of today's session is hysteresis. So what is hysteresis? Hysteresis is nothing but lagging of magnetization. Lagging of magnetization behind the applied magnetic field. Lagging of magnetization in a ferromagnetic material behind the applied magnetic field is called hysteresis. So generally when we apply magnetic field, what happens? Magnetization takes place. So that magnetization does not follow the applied field. That is what is called lagging. Because of lagging, what happens? That we are going to discuss in this particular topic. Now, hysteresis represents loss of magnetization during a cycle. Hysteresis represents the loss of magnetization during a cycle of magnetization. So finally, due to this phenomenon, loss in a ferromagnetic substance takes place. So because of this hysteresis phenomenon, ferromagnetic materials have so many applications. Right now, so how we have to discuss hysteresis phenomenon. So now we are going to discuss this phenomenon by plotting a graph between applied field, which by taking on x-axis, and magnetization on y-axis. You can call it as magnetic field induction also, magnetization or magnetic field induction. This is the x-axis parameter, what is called applied field. So when the applied field is 0, the magnetization in that ferromagnetic material is 0. Means all the domains are in the random positions. Magnetic moment of one cancels with the other, so that the net magnetic moment is 0. When we increase the magnetic field, what happens? The magnetization takes place initially by domain displacement. So those domains which are orienting in the favorable direction of magnetization will increase in size. That is, magnetization starts. Further increase in magnetic field, magnetization takes place. That is how the curve will take the path. So this is finally we can understood here at high field, all the domains will will be in the direction of applied field. This is applied field which we are taking from left to right, and this is the arrow mark which we are observing here. By seeing this, we can understood that all the domains in the ferromagnetic material attain the direction of the applied magnetic field. That is how magnetization takes place in a ferromagnetic material. So based on that previous information or basics, now I am going to explain this hysteresis curve. So as I told that hysteresis is the phenomenon that is associated with ferromagnetic materials. It is studied between the two parameters. One is applied field on x-axis and magnetization on y-axis. Initially when applied field is 0, magnetization is 0. When we increase the applied field, some domains will respond and magnetization takes place. At a particular point A, if we remove the applied field, what happens is all the domains will come back to their original position and they will follow the same path. That is why this particular region is named as reversible domain displacement. Reversible domain displacement, because when we remove the applied field, magnetization decreases in the same path as that when it is increased. Now, from point A, when we increase the applied field, what happens? Further, some more domains will come to the applied field direction, orientation takes place and magnetization takes place up to point B here. So, at point B, if we remove the applied field, domains will not come to their initial position. They will not follow the initial path. That's why it is called irreversible domain displacement. Irreversible domain displacement. Now, what happens when we further increase the applied field after point B? So, almost all domains will come into the direction of the applied field, and finally magnetization reaches to a saturation value here. Magnetization reaches to a saturation value. Now, at this point C, when we remove the applied field, what happens? Actually, when we remove the applied field, it has to follow the same path actually, but it will not follow the same path. Means demagnetization does not take place in the initial path. It will follow some other path. That is, rate of decrement is different as that of rate of increment. That is what is called the phenomenon called hysteresis. That is what is called lagging of magnetization behind the applied field. Now, finally, when we decrease the applied field and magnetization is following different path, and finally it reaches this point. This point is called BR, remanent field. So, what is remanent field? Remanent field is nothing but the amount of magnetic field retained in a ferromagnetic material even though the applied field is decreased to 0. Even though the applied field is decreased to 0, some sort of magnetization remains in a ferromagnetic material. That is what is called remanent field. Now, what we have to do to decrease the remanent field to 0? We need to apply magnetic field in the reverse direction. The reverse value of magnetic field that is required to decrease the remanent field to 0 is called critical field. So, here HT stands for critical field. The amount of reverse magnetic field required to decrease remanent field to 0 is called critical field. As it is negative, it is taken as minus HC, or we can call it as reverse field instead of the sign. Now, further increasing magnetic field in the reverse direction, magnetization also decreases, and finally it reaches to the lowest saturation value, minus B saturation. Further increase in magnetic field, it will follow this path. Again, it will cross the curve at this point. Again, further increasing the magnetic field, finally it reaches. Finally, we are getting one loop here. This is called hysteresis loop. This is called hysteresis loop. So, by taking a ferromagnetic material, when we study its magnetization versus magnetic field or applied field, we will get this type of curve. So, what to understood? This is actually the curve. This is the initial position, saturation magnetization. Again, finally we are getting one loop here. This is called hysteresis loop. That is what we discussed in the previous slide. So, based on the hysteresis loop area, this loop has some area. Based on the hysteresis loop area, ferromagnetic materials are divided into two types: soft magnetic materials and hard magnetic materials. So, that is what we discussed in today's session about ferromagnetic materials. What is ferromagnetic material and what are its special properties, and what is the special phenomenon that is associated with ferromagnetic materials? That is, we discussed about its hysteresis phenomenon. It is because of the domains that are present inside the ferromagnetic material, and due to that they have so many applications. Also, some of the applications we mentioned. And finally, based on hysteresis loop area, all ferromagnetic materials are divided into two types: soft magnetic materials and hard magnetic materials. Both these soft and hard magnetic materials have their own applications in different fields that we are going to discuss in the next class. Thank you.